to be audible over there. It's okay like this? You have it on this?
Yeah, on the right side.
Okay.
You and the right
I'm
side.
going to post the video on the web. Very good. Welcome everybody. I want just to see, so there is one chair. Okay, first of all, you guys are some students live, but so is the administration. So, are we taking some chairs from the outside room? Did someone bring in some chairs from not this room? They claim that the reason why we can sit everybody is because we store chairs from elsewhere. I could not care less just in chairs, I just want to know if it's the case. Did we took some?
Yeah, last time.
Not this one though? And I see that there is one, someone just took it. There is one empty chair here. I'm just trying to convince the administration that we are not breaking fire code. Yeah, we are a little bit, not too much. Your questions, go ahead.
Microphone turned down a little bit.
Okay. Yeah, no problem. Thanks for telling me. Well, now it's useless, right?
It's like all or nothing.
Yeah, exactly. And I'm at like 98%, so. What, sorry? Okay. Here maybe. Is it any better? Can you hear me? No? Kind of? I mean, through the microphone. Ooh. Sorry. Well, we'll do our best. That's weird. Any questions about any of what we have talked about so far? Very good. Well, we can just keep going and do this lecture, I guess. So, the way this class is organized is that at the beginning, I had a little bit of historical stuff. Then I talked about how evolution works in very general terms, using as a model the HIV virus, the evolution of the HIV virus. And then now we're going to go through a few lectures about various topics to try to have an idea of how some tools are being used. And then we will go into microevolution, which is the evolution of populations and individuals. And then we will go into macroevolution, the big picture, how you get elephants and dinosaurs and stuff like that. So this is sort of nuts and bolts kind of lecture, which is the kind of things that I like, because I have a better understanding of how things work when I look at these things. So today we are going to look at phylogenetic inference, which is how you are going to make trees that are going to link together organisms, and indirectly it is also evidence for evolution. If evolution was not working through the mechanisms that I've talked about so far, organisms would not be linked together. They might have emerged through spontaneous generation in different places and in different times, and then would have changed independently. Instead, as it turns out, life on Earth is all stemming from a single root. It's quite fundamental in understanding what life is, and I assume that life has emerged many times, but I suppose that only once it worked all the way to where we are at right now, which is really interesting in itself. Phylogenetic inference is a way to find methods to reconstruct that history. If I can hear the feedback, you can probably hear it too. So I'm going to try to do this. Good. So this is the notebook of Charles Darwin. So I'm actually not very much into tattoos at all. This is because I kind of like to look at tattoos, but I'm not very much into tattooing myself, and I cried a lot when my daughter showed up with her body covered in tattoos. But that's another story. So she said, I've got bad news and good news for you. The bad news is that I've got tattoos. The good news, that's a bunch of fish. people have been trying to recreate the tree of life, that is to put all organisms into a phylogenetic context. If you follow the logical explanation of what evolution is by Darwin and Wallace, you would theoretically be able to make a tree of life where every single individual organism on Earth could fit within a tree. This is what is called a tree of life. People have done it and it does work. So I won't go into the details because really this is a little bit beyond the scope of this lecture, but the bottom line is you can actually make a tree, you can represent them however you want, but when you have a very large tree, it's a little bit easier to represent it as a circle because then it fits better. Oh, I have a friend that has this tattoo on his back. I'm trying to take a picture and put it next. But anyway, and it looks a little bit like this. It does work. You can put pretty much any organism on Earth in a tree and it actually fits wherever it's supposed to come out. So there is a number of theoretical complications in building this kind of trees. It's very, very interesting. Again, it's a little bit beyond the scope of this class, but if people are interested, I don't mind talking for a long time about these kind of things. What I find powerful in what I'm going to talk about today is that phylogenetic methods, which is the methods to reconstruct trees, do not have specific taxonomic ranks. And what I mean by that is that the tree that I showed a second ago is a tree of life, where all the organisms are in it, but you can also make a tree of all the mammals, or you could make a tree, in this case, of all the dogs, meaning all the wild dogs and the domesticated dogs, or you can make a tree of just all the types, varieties of domesticated dogs. Or you could make a tree of all the Rhodesian ridgebacks or something like that. So the methods that I'm talking about are not restricted to a specific group of organisms or to a certain taxonomic level. That's why the approaches are very powerful, because they are universal approaches that work for everything. Charles Darwin has a single figure in The Origin, in his book, The Origin of Species by Means of Natural Selection, and it's a phylogenetic tree, which some people claim he stole from Wallace. I won't go there. Just, if you're interested in it, Google that, and you will have books and books of people that talk about these kind of issues. But the fact that a single figure in his book is present, and that figure happens to be a tree, means that he considers that it's probably an important topic. If you believe in evolution by means of natural selection, and you consider that all life stemmed from a single origin, you should be able to use evolutionary theory to then make a taxonomy that is paired with evolutionary history, meaning all the mammals should be together, all the birds should be together, and so on and so forth. And so that seems simple enough and logical enough, and that's the right thing to do. The problem is that it is actually very difficult to do in very practical terms. In the old days, people would be knowledgeable and they would put together organisms, but they didn't know how they would fit in the big picture. And this is because they didn't have the tools to make a proper phylogenetic tree. The Origin was published in 1859, and the first tools to make phylogenetic trees came out almost a century later. This came about with Willy Hennig, who was a German scientist, and he came up with a theory of a philosophy of phylogenetic inference that is called cladistics. You may have heard about that. There is, again, books and books written against cladistics and saying that it's terrible and stuff like that, and there are a lot of problems with cladistics. The bottom line is, it's actually pretty incredible. It's very, very good. It is marred with problems, but looking at problems is forgetting the big picture, and the big picture is that with cladistics, for the first time, people were able to go from the idea of using evolution to do taxonomy into an actual workable model. So this is really great. Again, I'm not at all saying that cladistics is incredible, universal, fantastic, and so on. I'm just saying for the first time people were able to do something really good. Willy Hennig himself was a really interesting person. He worked a lot on herbs, meaning flying snakes, gliding lizards, but his forte was in insects, in flies mostly. And he wrote his theory while he was in jail. He was a prisoner of war during the Second World War. He worked for the German army, so he worked for the Nazis. A number of things have been written about him to know if he was a Nazi sympathizer or not. After reading a little bit about it, I have the impression that he really wasn't, so there is no need to sort of sort his memory, but he definitely was an outstanding scientist. So, the idea of cladistics is to take the philosophy of evolution and use it to classify organisms. And so you need to have a way of describing what you're going to do, very practical tools, and this needs to work for everything, and it needs to be really simple, and it needs to work at any possible level. It works at the level of a family, it can work at the level of a genus, of a class, a phylum, whatever. And so he came up with the idea that you are going to define what is called a clade. In the midterm, there is no way I'm not going to ask the question, what is a clade? So you should write it down. It's really important. So, because the principal fundamental unit of his method is called a clade, the entire method is called cladistics. That's where the word cladistics comes from. A clade, sadly, has also other names, and it is sometimes called monophyletic group, sometimes it is called natural group. It sucks, just live with it. There are three ways of saying exactly the same thing. I'm sorry about that. And so the opposite of monophyletic would be non-monophyletic or paraphyletic or polyphyletic, whatever. Natural group would be unnatural group, so if you're not in a clade, you're an unnatural group. But some people, and myself, that I use the three terms completely interchangeably. And that's just how it is. Okay, so how does it work? It works in the following way. For what you're going to try to do is to classify organisms and bring them together to make a cluster. So you're going to say these organisms are more closely related to each other, evolutionary speaking, than others. All the rodents are different than elephants. And so what you're going to try to do is to group together organisms, and these groups are going to be called a clade. And a clade is a group of organisms that, evolutionary speaking, is more closely related to each other than anything else. And so to define what a clade is, you need to fulfill two definitions. And so these are the two definitions that you need to know. The first one is that all the individuals in the clade derive from a single ancestor. Because the fundamental philosophy of the method is that you want to follow evolution. Well, in evolution, you need to have a single ancestor, and that's why you are together. And so that seems pretty logical. All the individuals in the clades derive from a single ancestor. There is a second definition of it, and for a clade to be fulfilled, both definitions need to be fulfilled. The second one is these ancestors' descendants are all within the clade. Now, these two definitions seem obtuse, confusing, and redundant. And so I need, instead of saying the definitions, to show you an example to explain what I mean by that. And then it will become, hopefully, crystal clear. Now, I know that I'm completely biased. However, the best way to explain this concept is to use fish. Sorry, once again, they rule. Okay, so there are two definitions. all individuals in the clade derive from a single ancestor. So now I'm going to just tell you a fact. I'm not going to ask you a question. I'm just going to tell you a fact. All fishes in the world derive from a single ancestor. There is one ancestor, and fish derive from a single ancestor. And so the first definition is all individuals in the clade derive from a single ancestor. So fish fulfill the first definition of the clade. The second definition of the clade is these ancestors' descendants are all within the clade. Let me explain what that means. So here you have fish. The problem is that some fish are more closely related to tetrapods, which are mammals, birds, and reptiles, than they are to other fishes. So this means that if you take what stems from this ancestor, not everything is fishes. You have both fish as well as tetrapods. And so because of that, fish do not fulfill the second definition of a clade. This ancestor's descendants are all in the clade. So the question is, are fish a clade? The answer is no. The reason why the answer is no is because they fulfill the first definition, but they don't fulfill the second one. The second definition is that what came out of this ancestor should all be within the clade. And the answer is no, because we don't have just fish. We also have tetrapods. And so in the old days, before cladistics, fish that look like those swimming things that go around, people say, well, this is a group. And so they had a biological term for this, and it used to be called Pisces. But that definition fell with Willy Hennig's way of doing cladistics, and so fish are not in a clade anymore. So either you say, well, everything is a fish, including us, which would be great, and I'm totally fine with it, but most people do not accept that. And there is a great book, by the way, it's called Your Inner Fish, I think it's called. I think that's the title of the book. I read it, it's fantastic. It explains how we are related to fishes. But another way more common to use is to call fish fish with a small f, and it's just an English term, and just to say that fish are not a monophyletic group. They are not a natural group, they are not a clade. Some people in this class have taken my fish class, so they've heard all this, they know it just as well as I do. For people that have not taken the fish class, I have a question. Does anyone here that has not taken the fish class know what kind of fish are here? Do you guys know what kind of fish are more closely related to us than they are to other fishes? Maybe you didn't know that some fish are super close. That's right. The general term is called the lobe-finned fishes. The sarcopterygians is the lobe-finned fishes and us. That's right. Okay, another question is, what kind of lobe-finned fishes are there out there? Does anyone know what the name of some lobe-finned fishes are? One is pretty good to eat, the other one is not very good to eat. I don't know if that helps. But... Go ahead. Coelacanths and... Oh, so you have to write this day in your things because you just learned something that is amazing, and the fact that you've lived that long without knowing this shows me how bad the high schools are in California. Lungfishes and coelacanths are more closely related to us than they are to all the other fishes. They are. I had a pet lungfish for 16 years. It's dried up in the lab right now. It was awesome. It was super great. They are amazing pets, really fun pets. A friend of mine quit smoking because of his pet lungfish. The lungfish was coughing all the time and he was smoking. So he had to quit smoking. It's true, it's a true story. So they are beautiful pets. So because of lungfishes and coelacanths, fishes are not a clade. So another thing that is powerful about clades is that, as I described earlier, clades are not at a certain rank. So I I mentioned that they work for a genus, a family, an order, a class, a phylum, whatever. And for example, tetrapods are a clade because within this group here, within the group of tetrapods, that is a clade. Humans are a clade, mammals are a clade, birds are, and so, however, fishes are not. So that allows you to group together organisms. So, in a sense, I just now described what a clade is not, but clades do exist, of course. As was correctly stated by one of you guys, the group of these guys now are called sarcopterygians. Sarcopterygians is tetrapods together with those fishes that are lobe-fin fishes. This was idealized representation of what it looks like. Don't take my word for it. People have actually sequenced all the genomes of not all the genomes of representatives of all the different vertebrates. And this is shown here, where coelacanths and lungfish group together with the tetrapods. And instead, these guys are the ray-fin fishes. So in green, you have a clade that is the ray-fin fishes, and in purple, you have all the sarcopterygians. One of the things that is super cool in this paper, this was published in Nature maybe 2 years ago, is the person that is used to represent humans is a person called Marjorie Courtney-Latimer. She's the person that discovered the first live coelacanth. So I think it's kind of a cool touch. It's super nerdy.
Just like grammatically speaking, is a clade always going to be capitalized? Like if we're
Oh, no. No. I capitalized it maybe, but it was just to emphasize that it was. No, not at all. It is not a clade. That's an important question. The clade is not a taxonomic rank. It's a way of, it's exactly like if you were to use the word cluster. A cluster of organisms. A clade is like a cluster with the difference that it has also not only a biological meaning, but also to be a clade, you need to fulfill those two definitions. So not a cluster could be, a cluster of, I have a frog and an elephant. That's a cluster, but that's not a clade. No, you don't need to capitalize it. Yeah. No. A clade can actually, strangely enough, a clade can be actually made with a single species. Because a single species may have many individuals, and also because some species may be extinct, and so the only living organism can be a single species, but it can still make a clade. Yeah. Okay, so that's great. That is sort of the general idea. Now, how do we, in very practical terms, come up with a clade? And so now I'm going to move into the nuts and bolts of how you're going to actually make a clade. So, first of all, you make a tree. Here I show, when you represent a very simple phylogenetic tree, usually you take 4 organisms because it's a little bit easier. And first, you need to describe what is ancestral and derived characters. So, I don't really state it because, in a sense, I don't need to state it. However, you guys probably imagine that if I make a tree like this, this would be a phylogenetic tree. This is A, B, C, D. If I make a tree like this, even if I have not really said it, what you know is that this is what is old, this is what is new, and there is some sort of a time scale that I don't ever draw, but is here. Time is like this. So I've not stated it, but this is the reality of it. And so another big concept of Hennig that I'm not going to really develop fully now because it's a little bit complicated, but it's the idea, what he considers polarization. A polarized tree, this tree is polarized, it means that there is a root, and then These are called stems, and they use those sort of analogies to actual trees. I don't know if, is this too high for you to see this? Kind of, okay, you can keep it up. So this is a root, and this is like this. And the way he polarizes it, it's really important, because just to give you an example, if you take giraffes, I'm terrible at drawing, so I'm not going to draw giraffes, but imagine that here there are giraffes, and so I assume that at the bottom of a tree, there must have been some sort of antelope or gazelle-looking things with a shorter neck, and then later on the neck sort of grew. And instead, if you didn't have a root, you wouldn't know what is ancestral, what is old, and what is new. And so you would say, well, maybe the old state, what is called the ancestral state, would be a long neck, and then the leg shortens. Instead, if you have a polarized tree, you realize that the giraffes with the long necks are at the top, and then you say, okay, it started with a short neck, and it ended up with a long one. This is a crude example that is really obvious, but there are some cases where you see a character and you have no idea if this is ancestral, which is old, or derived, which is new. In the old days, we used to be calling it primitive and evolved, but that's not very PC, so now we say ancestral and derived. Ancestral is down here, derived is right here. So how would you root a tree? The solution that was used by Hennig is that you need to find something that is here that anchors your tree down below, and so you use what is called an outgroup. An outgroup is an organism that is really closely related to these guys that you are interested in studying, but is just outside. And so the idea is that any character, molecular, morphological behavior, that is in common between this that you're studying and this, is probably a character that used to be in common in the ancestor, and because of that you actually can anchor here and you know what the ancestral state was. Let's say these ones are all the different species of giraffes. Now giraffes are actually 7 species, and this one is another antelope that is closely related. Then you can imagine that the old one probably had a short neck, and you polarize your tree. So the method of the outgroup is the most commonly used method to find, to polarize a tree. What is old is called ancestral, what is new is called derived. As a question that I like to ask just to wake you up in the morning, let me see if I correct it. The tree of life has 3 main, what are called domains. There is eubacteria, which is what we call bacteria. There is the archaea that used to be called sometimes the green algae, blue green algae, stuff like that, the archaebacteria. And then the eukaryotes, including ourselves. This is the 3 domains of life. All life on Earth fits in this tree. The tree is separated into 3 domains. Because the tree is rooted, the root is here, we actually can tell that these 2 are closely related. We are more closely related to archaebacteria, archaea, than we are to eubacteria. However, the reason why I'm saying this is because I know that the root is here. If I didn't know that the root is here, then the tree would look something like this, and there would be eubacteria and archaea and then eukaryotes, and we wouldn't know where the root is. The root happens to be here, but if the root were here, then eubacteria and archaea would be more closely related and so on. So placing the root is actually quite fundamental in understanding how the trees work. Now, this tree was actually made in such a way that they used an outgroup to outgroup this tree to find where the root was. And so it's not exactly a trick question, but it's a very difficult question that I'm going to ask now. And is, does anyone know what was used to root this tree? not only is the question complicated, and I'm going to go give the answer, probably most of you will not even understand what the answer is, but nevertheless, it's kind of cool. You can say anything silly because I've heard it all. So the question is, you have a tree of life, you need to find an outgroup to this tree of life to be able to find where the root is. Would anyone facing this problem come up with an idea for the root? I hope that you know the answer because I said it in my class that you've taken before.
Oh, now I'm ordering this.
Yeah, you should. If you're not 100% sure of your answer, I'd be super disappointed. You can say silly things. Because no one else has any idea whatsoever. You guys are, what's that? Amino acids. So somewhat, I mean, this tree is not really, it's not exactly a tree that is made with amino acids. So I kind of understand what you mean by that, but that is not the way they did it. Go ahead. So anything that is a bacterium goes in here. Go ahead. These are good ideas.
Maybe a virus.
A virus. That is a good answer, but that's not the correct one. Go ahead.
Is it mitochondria?
Nope. No, they go in here. Go ahead. Single cells, they are anywhere in here. No, this is not the way to, again, now this is your chance.
I'll try. Is it protocell?
Nope. But that was a good idea. Oh, go ahead. Kind of. The way they did it, oh, go ahead.
I was going to say the primordial soup.
Sure, if we had a remnant of that, we could, but we don't. The way they did it, I mean, it is really super nerdy, but the way they did it is that this phylogeny was made with some very ancient genes, and the way they did it is that they found genes that had duplication before this happened. And so they sequenced the two pairs of genes, not the two pairs, but each individual gene in the pair, and then they make two trees that look the same, and they are rooting each other. So there are two trees that are rooting each other, and the fact is that these are the two same genes, and the duplication of the gene happened before the split. So very, very early on in the origin of life, some genes emerged, those genes duplicated, and after they duplicated, the tree of life started. And so you can actually take these genes, sequence both of them, and you take one gene and you root the tree with the other one. It's, again, it's kind of nerdy, but it's kind of cool. Okay, let's go back to evolution. Well, it is evolution. So, ancestral versus derived characters. So the two main contributions to the field by Willy Hennig, one is cladistics, and the other one is that he understood that it was really fundamental to understand evolution to polarize trees, and his idea was to use outgroups. So now, you have different types of characters. These characters can be morphological, behavior, genetic, it doesn't really matter, but they are just characters. And these characters can either be at the tip of a branch of a tree, these are called branches. So when you have a character that is at the tip of a branch, meaning that only the very latest organisms have that. For example, if you take the trunk of an elephant, well, things before the elephants don't have trunks. So it's really something that happens at the very end of evolution. It is called a character, so it's the word is morphe, and because it's at the tip of the branch, it's called an apomorphy. Apo means at the tip. So an apomorphy is a derived character. Those characters are kind of cool, we like them because they define what the species are. However, they are useless for taxonomy because the goal of taxonomy is to group together organisms. An apomorphy does not allow you to group an organism, just the opposite. It allows you to distinguish that organism from others, but it does not allow you to group them together. What you want is to be able to put together all the rodents. You don't want to know that, a gopher is different than another one. That's not the point. What you want is, what are the characters that are going to allow me to put together the organisms into a clade? And so, instead, you're going to take shared derived characters. Shared is syn, S-Y-N, and an apomorphy is a character that is derived. So a syn apomorphy is a character that is found in multiple organisms. And the philosophical idea behind it is that if this character is shared among organisms, most likely it was also present in the ancestor. That's the simplest explanation. Of course, there are exceptions, but the simplest explanation is that that character was found in the ancestor. That is what is represented as this red bar right there. And so it's found in A and B, and so most likely it was also found in the ancestor of A and B. This is a synapomorphy. A synapomorphy is what defines a clade. If you find a synapomorphy, you can define a clade. Okay, question. Can anyone here, I'm always focused on fishes, I'll stop apologizing in just a moment. So, can anyone here come up with a morphological character? I want to ask you about genetics. A morphological character that is found only in fishes and in all the fishes. Can you think of a character that is found in all the fishes and only in fishes? What is it? Gills? Not gills, because it's found in some, some salamanders and some amphibians. Right.
This is just a get but the air sounds like a
The gas bladder. The gas bladder is found only in later on in the life of fishes. The primitive fishes don't have that. Go ahead.
Wouldn't there be nothing because the fish?
Of course. Absolutely, that's the correct answer. The answer is no. Because it is not a clade, you cannot find those characters. So, synapomorphies define clades. As we have just said, fishes are not a clade, so you cannot find those characters. That was a trick question. And I was able to trick only a few people, so that's good. You are in good company. Hundreds of people have incorrectly answered this question. It's some sort of stuff that keeps me awake on Monday morning. No worries. Phylogenetic trees are built. However, as much as I ask questions, I very much appreciate you coming up with things, because it's only when you think through potential answers that you can really move forward and I'm not falling asleep. So I'm extremely appreciative of anyone who says anything, very much so. This morning, I had to wake up my son like 15 times. He was so asleep. It drives me crazy when I see apathy in his. But he's pretty cool still. Anyway, phylogenetic trees are built from characters. Characters can be morphological, behavioral, physiological, or molecular. So just to re-summarize what Willy Hennick's contribution to the field is, he comes up with the idea of clades. He defined how you make a clade. You make a clade by finding synapomorphies, and he came up with the idea of polarizing trees. You need outgroups to polarize trees. There are two important assumptions about characters that are used to build trees. One is that the characters are independent. If you use dependent characters, then you're always doing the same thing. And the other one is that they are homologous, meaning the characters have to be comparable. And I'm going to explain what I mean by that in a second. So, now that I made I said that cladistics is so fantastic and so on, I'm going to talk about the pitfalls of the method. Go ahead.
What is a behavioral character?
A behavioral character is, let me give you an example that is so incredibly cool, I think. So there are people that have studied frogs. I know very little about frogs, but this paper I thought was really interesting. So what they did is that they have species of frogs, and they made a phylogenetic tree of different types of frogs based on behavioral characters that are the songs that the males do to attract the females. And so the tree is not based on genetics or on morphological characters, it's based on behavioral characters, which are the songs. So they have a tree that is really complicated and is something like this, and you have all these different songs, right? And so they have this complex of frogs that have different songs, and what they do is that they record the songs, and then they play them back to the females, and the females are attracted to the songs of the males of their own species. However, when you play the songs of males of a different species, the females are not reacting at all because the females recognize the males of their own species. So what they did, which I thought was really cool, is that they took the song of this species and this species, they digitalized the songs, and then they were able to identify in those songs the common patterns of the two songs. And they assumed that the common patterns were the patterns that were found in the ancestor of these two species. They played this pattern to the females of each of the two species, and the females were attracted to this song. So they were able to identify, using a behavioral tree, what was the ancestral song that would work for each one of those two females. But now that they had diverged into two different species, the females did not recognize the song of the other species. So that's one example of a behavioral tree. What are homologous characters? They are shared by two species because it was inherited from a common ancestor. This is what would be called a synapomorphy. And it is not present in other ancestors. A character possessed by two species but was not present in their recent ancestors, it is said to exhibit homoplasy. And so now I'm going to explain what type of homoplasies there are. Homoplasies, I'm sorry, it's a technical term, but it's a term that you should know. When I say that, it means that more likely than not it will be in the midterm. So just write down homoplasy, what is it? I'm going to now explain what a homoplasy is. Right now I'm explaining what the pitfalls of cladistics is. That is, when are we in a situation where cladistics seem incredible and actually they really do not work? And the classical example of a situation where cladistics do not work is when homoplasies are present. There are three major categories of homoplasies. These are characters that fool cladistic methods. The first one is convergent evolution. I'm going to list them now and then I'll give you examples. Convergent evolution, there we go. Convergent evolution. Evolution of eyes, flight. Flight is the most commonly used example. If you look at the wings of a bat, of a bird, and of a cricket, all three organisms are flying. However, the origin of the wings is very different. And if you were to just look at cladistics, you are an alien, come on Earth, you say, you know what, I'm going to use cladistics. How am I going to group the organisms together? Do they have wings? The answer is yes. Oh, okay. Bats, birds, and insects should be grouped together. Obviously, this is due to convergent evolution. They all fly, so there is a convergence. These are not characters that derive from a common ancestor. This is one of the pitfalls of cladistics, where you call a synapomorphy a character that is only due to convergent evolution. This is a homoplasy, one type of homoplasy. The other one is the evolution of the eye. The eye in octopus is different, evolutionary speaking, than our own eyes, the eyes of vertebrates. The eyes of vertebrates and the eyes of octopus did not diverge from a single eye ancestor. It's a convergent evolution. We both can see very well, but it's not due to our convergence. Go ahead.
Or to the vertebrate, so all vertebrates, is it from a...
Yes, all vertebrates have the same origin, but not invertebrates. Yeah. Another example is animals that have similar, I mean, you have so many examples, I'm sure that you know tons of them, I'm just stating some just because. And it's organisms that have similar ecologies. The thylacine, or what is called the Tasmanian tiger, that is now extinct, maybe, is this guy right here. Then there's the fossa, one of my favorite organisms that feeds on small tasty lemurs in Madagascar and scares everybody. That's a mongoose. And then the mountain lion. All these guys, if you didn't know much about them, you would think that they are grouped together, while in fact they are very, very different, completely different organisms. I mean, not super, they are mammals, but they are not the closest relatives. However, because they have similar ecologies, they have more than one character that is similar, very much like when I talked about flight. If you look at flight, the wings of birds have bones that are very, very light, and so are the structures of insects are very, very light because you need flight. Here is the same thing. These guys have similar ecologies, so they have very powerful jaws, they have a long tail to allow them to balance themselves, they are very strong because they're running and they're ambush predators, these kind of things. So it's not limited to a single character, sadly. But this is convergent evolution. Marsupials and placental mammals have a lot of examples of convergent evolution. These are pairs of mammals that are not each other's sisters.